Okay, welcome back everyone. Let's talk about trig identities. Now we're going to go through some basic identities, usually in a section on identities. If you look at the exercises in a typical trig book, you get at least 30, 40, 50 different identities that you work through and show the left and the right side are the same. Going forward, like in your calculus, well, you're not going to work with these crazy identities that you probably never see in a lifetime. But I tend to work with the ones that are going to stay with you going forward in your calculus and higher courses. A certain number of identities repeat themselves. Okay, so I'm more focused on those than some crazy expression that simplifies to just sine x in the end, or 0 or 1 or something like that. So let's begin with the idea, what is an identity? What is an identity? So an identity would be something like this: f of x is equal to g of x. We say that this is an identity provided the two functions are the same for all x, okay, for all x in their domain. And that's all an identity is. It's just an equivalent expression. Okay, so for instance, for example, an identity would be this. Let's say I have 2x plus 1 in parentheses is equal to 2x plus 2. Now if I try to solve this for x, and notice the domain of this function, all real numbers, domain of this one, all real numbers. So let's take a look and see what happens here. We get 2x plus 2 equals 2x plus 2. Subtract 2x from both sides, and I get 2 equals 2. The variable is gone. I have a true statement, right? So this is usually the sign that the equation we have is an identity. Okay, so this is an identity. In all, we have 3 types of equations. An equation can be an identity, just like the one that you observed. That means it's true for all x in the domain. The equation could be a contradiction. Contradictions have no solution. Or it could be what we call a conditional equation. An example of contradiction would be this. Let's say I have 2x minus 1 equal 2x plus 5. Subtract 2x from both sides, negative 1 equals 5, and that's not true. This is false. The sign of a contradiction. Okay, we don't care about contradictions either. Now conditionals we work quite a bit with, right? So let's check out this one. Let's say I have x minus 1, x plus 3, x minus 7 equals 0. So by zero factor property, I get 1, negative 3, 7. I pick up 3 solutions here, don't I? Well, as long as I have a finite number of solutions, then this equation is a conditional equation. It only works under these conditions. It equals 0 when x is either 1 or 7 or negative 3. Okay, that's the same idea works with trig functions. So when we talk about trig identities, we're talking about the kind that we saw in here. So we can replace one expression with another expression without changing the solution. Okay, now we have already established quite a few identities, whether we know it or not know it, earlier in chapter 6. In fact, let me real quick flash. There you go. Right down here. There you go. See these identities? We have already talked about identities. We talked about, I believe, 7 or 8 of these, right? There's 3 of them, the reciprocal identities that we will work through. So I would like to recall these. We have the ratio identities for tangent and cotangent. We will be using those. And we have, again, the all-purpose Pythagorean identity here. And we have the byproducts of Pythagorean identity, those that involve secant and cosecant. And then we have about 6 of these, the negative angle identities. And again, I want to recall, for all trig functions are odd functions, so that means the trig measure of negative angle equal negative of the trig function of a positive angle, with the exception of cosine and secant. So all the other 4. Remember, we have 6 so far total. So of the 6, 4 of them are odd. 2 of them, cosine and secant, are even. So whether you change negative to positive, theta does not matter, but it matters for the other 4. Okay, so I'm going to keep this here in case I need it. I'll refer to it at a later time. That was easier than just writing these or rewriting them for you. So let's actually go through and see how we're going to do this. Now, one thing I want to point out again, because with identities, it depends on who does the identity, they may do it differently. When we say, the keyword is establish. When we say establish an identity, that means you need to build a process in which you go from one expression to the next expression. So let me go in the algebraic form of this. Suppose I have x plus 2 squared over x squared minus x minus 6. Okay, now I can factor the numerator. What I'm doing is I am working with the left side. Notice we don't know what the answer is on the right side, do we? In the case of trig identities, they give you the answer on the right side, and we're supposed to work toward the answer, and that's the point I want to make. When we say establish the identity, that means you work from one side, typically from the left to go to the right. Okay, so I'm establishing this answer, the identity. Notice I don't know what the answer is yet, so I don't have the right side. I'm building it as I go. This will be factors as x plus 2, x minus 3 in the denominator. They cancel, and there you go. Oh, okay, so I can say, oh, that's an identity for this expression. So if I was given something like this, it's like working with the answer and going back to the problem. All right. So to me, when they say establish, means you work from left to right. And that's how I'm going to do my identities. I'm going to work them from the left and simplify them towards a final answer, because that's what really we would like to do with these identities. We would like to be able to write them as possibly a simpler expression. Now, here's what some people do. For instance, if this was a question that said establish the identity, people work on both sides of this. They work on the left and right at the same time. And even some people may do this. Check this out. So this is really not establishing it if I'm doing it this way. Suppose the problem is establish this identity. Okay, well, here's what people do. And even some instructors do it, which again, to me, establish means you simplify the left and show the equals to the right side. That's what that means. Now, people actually cross multiply these. And of course it's going to work, right? Because we simplified it. But I didn't really establish this anything. I just showed that that's a true statement without working toward anything. There you go. X squared minus x minus 6. I know that's going to work. Okay. So how is this equal to that? Well, x plus 2 squared, you can write as x plus 2, x plus 2, x minus 3. This is x plus 2, x squared minus x minus 6 is x plus 2, x minus 3. And you see, these are the same. So people do this kind of thing. And again, it's done all the time. I just want to again clarify. To me, establish means you work from left side and you show the right side. It's true. Okay, so let's actually do this and I'll show you what I mean here. Suppose I have cosine theta times tan theta plus cotangent theta is equal to. Now imagine this. If I didn't give you the right side and the question says simplify. This is how I solve my identities. It's as if I don't have the right side. Okay. So, in fact, I'm going to hold off on the question mark. And let's simplify. Let's simplify this one. So, I'm going to write, I'm going to distribute cosine to tangent and cotangent without knowing what the right side is. Now, tangent is the ratio of sine to cosine, right? Ratio identity. Cotangent is cosine to sine. And then what do we do next? Well, I can cross out the cosines here. So I get sine theta plus cosine square theta over sine theta. Now I can get LCD, correct? Multiply by sine theta, divide by sine theta. And now my LCD is sine theta. In the numerator, I get sine squared plus cosine squared. And we know what that is, right? That's 1. Pythagorean identity. And what is 1 over sine? The reciprocal identity for cosecant. And I'm done. And there you go. So in the textbooks, the questions will all be like this. Prove the identity that the left is that. And there you go. So really what you're proving is, I should probably better should say simplify. Simplify and here's the answer. Rather than proving the identity. Okay. I guess I made my point. So now let's continue on without all the dilemma. Let's say I have secant to the 4th negative secant squared theta. I don't know if I should give you the right side. Yeah, let me write down. So otherwise it's going to look too different than from the textbook we're using. You can say, that's not how the book says or does it. And there you go. So we want to establish the identity. I'm going to work from the left side. So I'm going to go from left to right. First, I can factor the GCF, secant squared. That'll give me secant squared minus 1. Leave the right side alone. Leave the right side alone. Now, the Pythagorean identity. Sine squared plus cosine squared is 1, correct? I need something that connects or brings secant and tangent into this. Well, divide by cosine squared. Every part. Now sine over cosine is tan squared. Cosine is 1. 1 over cosine is secant. And there you go. See? On demand. You don't have to memorize that. So I'm going to replace secant squared with 1 plus tan squared. So that's tan squared plus 1. Right? That's just secant squared. And then on the right side, I have secant squared, which is, again, tan squared plus 1 minus 1. The minus 1 is the second term in the binomial. These are opposites, they add to 0, right? And then distribute the tangent from the right. That's tan to the 4th plus tan squared. And there you have it. You see that? That is the right side. So that's how, let's say, this expression simplifies. Let's take a look at a couple of more. This one, suppose I have 1 minus sine theta divided by 1 plus sine theta. And this one, we want to show that this is equivalent to secant theta negative tan theta quantity squared. Okay. I mean, after all, have you ever wondered Where do they get the right side of these equations from? Correct? I mean, these are not like well-known identities. Most of them aren't. Most of them aren't. How do they know that? Right? Well, they really simplify the left side, manipulate it to a point, and then they stop at some point. They say, there it is. There is the right side. So it's really, trig identities are simplifications of the left side and form it into the right side. Okay, let's establish this one, quote unquote. So I'm going to work on the left side. Now the right side is kind of a clue as what they are thinking of here. To have secant, for example, secant, that's 1 over cosine. Tangent is sine over cosine, and I don't have a cosine on the left side, do I? So we do need to create the cosine. And here's how we're going to do this. We're going to multiply the top and the bottom of the left side by the numerator, or you can think of it as the conjugate of the denominator. Okay, 1 minus sine theta. And why, you'll see in a moment. Remember my strategy was this. Both of these have cosine on the bottom, and I don't have a cosine here on the bottom. So I'm taking actions to take cosine, and I know cosine squared is 1 minus sine squared. Right? And that is difference of two squares, and that's kind of my strategy for this one. 1 minus sine theta. And there in the denominator, I have the factored form of difference of two squares. So I'm going to write the denominator as 1 minus sine squared, which in turn gives me the cosine that I need. And it's okay, it's in squared form. Now in the numerator, we have two binomials that are the same. So let's FOIL them, distributive property. When you FOIL this, we're going to get sine squared theta, negative 2 sine theta plus 1. Okay, that's sine, you get sine squared. Negative sine, that's negative 2 sine, and then 1 by 1 is 1. All right. Now, the trinomial in the numerator, interestingly enough, we can write this one as 1 minus sine theta squared, right? Or you can write it as sine theta minus 1 squared. It doesn't matter. I like to go with 1 minus sine theta squared because of the way the answer looks. Now, let's combine the right side as one expression. So I'm going to put the numerator, and here's the denominator, the whole thing squared. Okay, so I have something like this, a squared b squared. I wrote it as a over b squared. That's what I'm doing. Now, let's, within parentheses, I can divide by the monomial cosine. Monomial means a single term. By a single term cosine, right? Quantity squared. And what is 1 over cosine? 1 over cosine is the reciprocal identity for secant. And sine over cosine is the ratio identity for tangent. And there we have that one. So I get secant minus tan squared. And that is the right side. So again, left side, we establish this. Notice that? We establish it. Now some people may do this. They're going to square the right side. They're going to multiply by 1 plus sine and show that that is 1 minus sine theta. Okay. But they didn't really establish it. They just said, okay, assuming this is true, then left and right are the same. I guess that worked for some. It doesn't work for me because to me that's not the intent of what identities were established for or meant to be. Let's take a look at another one. Cosine squared, negative sine squared, divided by 1 minus tan squared. And we want to show, see, There you go. When you simplify that, the answer should be cosine squared. Now, in this one, because it's only cosine on the right side, so I'm just going to change tangent to cosine. Over 1 minus sine squared divided by cosine squared equals. Now, one thing also, by the way, here's other people's recommendation. Again, I'm saying other people because I've done it, but I don't recommend it, as you can see, because that's not how I worked the example. For instance, this one. Notice the way I worked it. People say, well, change everything to sine and cosine. Change that to sine, cosine, and work it through and show that this is what it will be in sine and cosine. That's another strategy. So if that works for you, you can do it that way also. Here's an instance where I actually makes sense for me to change my tangent to sine and cosine. I think that's a better way of doing this business. Or alternatively, we can go to, let's see, tan squared to secant squared minus 1. Yeah, maybe I'll do this 2 different ways. They just recognize, yeah, maybe I can utilize that identity. I think I could. Okay, but let's do it this way. I'm working with the left side. Now, well, let's multiply top and bottom by cosine squared, because I have a complex fraction over a fraction. I'm going to multiply top bottom by cosine squared. So in the numerator is what it is. In the denominator is my focus. So let me just rewrite the numerator. And that's going to be what it was. Okay, divided by, in the denominator, I'm going to get cosine squared minus sine squared, right? Distribute. That's what I'll get. And then cross out the common factors, and there is a solution. Boom. See how simple that was? So that's one way of doing it. The other way, I just thought about, tan squared plus 1 is secant. So let me try this way. Here is option B, if the top one was option A. So I'm going to go cosine squared. Not sure where this is going to go, so bear with me. 1 minus, now tan squared, again, tan squared is secant squared minus 1, right? Minus secant squared minus 1. Negative 1 is positive 1. Okay, that's not going to work out that nicely. Cosine squared theta, negative sine squared. If it doesn't look good, I'm just going to stop to secant squared theta. Nah, let me forego this one. We did it this way. That was the easiest way we did it. So yeah, we're done with this. I don't want to make the video too long. So we're done with that example. Okay, and what else? Now let's do one last one. This one is a little different for this one. And the reason I'm doing it, because in calculus, some of these formulas involving, like this one in particular, you may see it in another alternate version. And let's say I want to simplify this using reciprocal identity, and this is ln of secant is 1 over cosine. And 1 over cosine, well, we can use properties of logs. Remember, ln of p over q is ln of p minus ln of q, right? So using quotient property, I can write this as ln of absolute value of 1 minus ln of absolute value of cosine. Natural log of 1 is 0, and you don't need absolute value on that anyways. But either way, it's 0, and you get negative ln of absolute value of cosine theta. And there you go. Again, this one is worth mentioning because sometimes you'll see this in some of the formulas for integration problems in calculus. And there you have it. So trig identities. I think we're good. It gets the point across, and hopefully you're able to do this. And remember, as much as possible, try to establish these rather than trying to work on both sides. And again, there are some crazy identities in this section in the book. You can try those if you like, but I think this will get the point across again for what's to come in your future courses. All right, and we are done with this lecture. Thank you for watching, and on to the next one. Take care, everyone.